Multiplexers. Let us define multiplexer. Multiplexer is a combinational circuit which has 2 to the power n input lines and only one output line based on n select input lines. So this is the general definition of a multiplexer. So look at here. So this definition, so I am going to draw a block diagram based on this definition. So let us draw. So it has 2 to the power n input lines. So let us call this input as a x0, say x1, x2, so on. X into 2 to the power n minus 1. So because here, look at here, 2 to the power n input lines are there. So I have started with x0. So in general, so it has, if you start with 0, then it is 2 to the power n minus 1 line. The last line is. So now I am calling this as a 2 to the power n is to 1 mux. So in short, multiplexers are also called mux. So there is only one output line, say output y. So I am going to write. So and it has n select input lines. So look at here, n select input lines. So start select lines S0, S1, so on. So once again it has started with S0. So the last line is Sn minus 1. So this is the general block diagram of an multiplexer. So multiplexers are also called data selectors. So and these select input lines, so I can call this, I'll write here, it is better, select input lines or select lines, or these are also called address lines. So particularly when you are dealing with microprocessor, so we are naming it as a address lines there. So now these are the 2 to the power n input lines. So these are n select lines or n address lines, and this is single output. So now based on this address, so any one of the input line that has been selected, say assume that, so if at all, so we are using n equal to 2. So n equal to 2 means it becomes 2 to the power 2 is 4, then it becomes 4 is to 1 mux. So at that time 2 to the power n input lines means 4 input lines. So that means it has to start with x0, x1, x2, x3 will become the 4 input lines, and there is only one output line y. So based on that address, so one of the input line is selected, so and the data on that line that has been transferred to the output. So this is the function of a multiplexer. So now let us deal with 4:1 mux. So I am going to draw the 4:1 mux. So 4:1 mux will happen whenever n value equal to, if you put 2 here, then it becomes 4:1 mux. So 4:1 mux. So let us draw its block diagram first. That means it has 4 input lines. Look at here. So this I will name it as a 4:1 mux. Now it has 4 input lines, 1, 2, 3, 4. So you can name these as D0, D1, D2, D3, or you can name it as a I0, I1, I2, I3 also. So now there is only one output line, so I am going to name it as a Y. So there are n select lines. So 2 to the power 2 is, so n value is 2, hence we have only S0 and S1 are the select lines. So S0 and S1, there are two input lines are there. So I can make here, look at here, 4 different combinations we can make. So S0 and S1 value, either these may be 0, 0, 0, 1, 1, 0, 1, 1. So based on these addresses, so one of the input line that has been selected, so and that value in that data input line that has been transferred to the output line. So now, so look at here, suppose, so my addresses are 0, 0, and S0 value is 0, S1 value is 0, so I0 line is selected. So whatever the data in the I0 line is there, that has been transferred to the output. So whatever the data means, here it is we are dealing with digital electronics. So your input may be either 0 or 1. So that either 0 or 1 that has been transferred to the output. Similarly, when your S0 and S1 line both are 1, 1, its value is 1, 1. So then I3 line is selected. So whatever the data in the I3 line is there, so that has been transferred to the output Y. So this is how the 4:1 mux functions. So based on this, we are going to draw the function table. So or it is also called truth table. So let us draw the truth table. So truth table of 4:1 mux. So let us draw the expanded version of this truth table. So it has select inputs, say these are S0 and S1. Then after that we have input lines. 4 input lines are there. One is I0, I1, I2, I3. So and there is a output. So that is nothing but Y. So now when my S0 and S1 both are 0, 0, so the I0 line that has been selected. That means if its value is 0, so the 0 is transferred. Suppose its value may be 1, so that's why I am writing one more condition. So that means it means 1. So now look at here, what about other lines? Other lines data may be anything. So that we are representing with don't care. So this X mark or cross mark is a don't care term in digital electronics. That means whatever I1, I2, I3 value may be. So meaning is that its value may be 0 or 1, whatever it. So based on the address, it only checks I0 line. So that is transferred to the output. So similar case here. So in similar way, so if you go through the another address, if it is 0, 1, so 0, 1, at that time your I1 line is selected. So if your I1 line has 0 data, 0 is transferred. If it is 1, 1 value is transferred. So similarly, going to another address, if its address is 1, 0, then I2 line is selected. If its value is 0, 0 is transferred. If its value is 1, 1 is transferred. So whatever the data in the other line may be. Similarly, when the address is 1, 1, so I3 line that has been selected. If the I3 line has 0, 0 is transferred. If I3 line has 1, so 1 is transferred. So this is the truth table for a 4:1 mux. So different books, they have given different ways of truth table representing. I hope better you refer this one. So it has enough amount of information is present in this truth table. So that's why I follow this method. Okay. So then after that we have to write the output expression. So we have to write the output expression Y. So that is nothing but Y equal to, we have to write the output expression. So by seeing wherever 1 is there, simply see the input lines. Then based on that you have to write that one. So here both S0 and S1 are 0, 0. So I have to write here S1 bar, S0 bar. So and its value I naught. So remaining are don't care, so don't consider that term. Then plus, so because one more one exists in the output column, so look at the inputs, again it is S1 bar because 0 is there, so I have to write S naught because it is 1. Similarly I1 plus, so proceed like way, so because one more one, so now it is S1 S naught bar I2 plus, the one more one is there last, go for this one, so S1 S naught because both are 1 1, again I3. So this is the expression, that means output expression for a 4:1 mux. So let us implement this, so using gates. So we are implementing using basic gates here, so it can be implemented using universal gate also, but for the basic electronics people, so implementation using basic gate is sufficient. Okay, so let us implement the same expression, because look at here, I need S1 bar S0 bar, also S0 S1 I need. So let us first draw S0 S1 then S0. So then I want a bar of this, means I will use one NOT gate, so I am getting here S1 bar. Similarly draw S0 and draw S0 bar. So these 4 lines will give my S0 S1 and its complements. So first one S1 bar S0 bar, then it has been with I0, so make the I0 line one more line here. So these are the input line and it is a AND operation, put the AND gate. Similarly proceed for other, so that means it is S1 bar S0 then I1, so use AND gate. Similarly it is S1 S0 bar, so put one thick dot, then connect, then I need I2 then use one AND gate, then S1 S0 then S1 S0 then I3, so use one more AND gate, so now in between plus operation means there is a OR gate required, so make one OR gate, so join all these to the input to the OR gate. So now this becomes Y. So this is the implementation of a 4:1 mux. So look at here, 4:1 mux. So now what I can say is that let us take one example. So let us take example. So let us say if my address is 10. So let us look at here. So my address is 10. So I am going to represent only one example. So later you analyze other. So if S0 and S1 are 10, so I need output Y as a, so which line has to be selected? So I2 line has to be selected. So look at here, based on if it is 1, here I will get 0, here I will get 1. So now one of the input line is 0, means output of the AND gate is 0. So that means here look at here 0. So here also I am getting 0. So here I am getting what? 1. So here also I am getting 1. So then here I am getting 1. Here I am getting 0. So based on that values I am writing here. So now one of the input line is 0, means these output irrespective of this I0, I1 and I3, the output will become all zeros. Look at here. So output will become, these values become 0. So only this NAND gate, sorry, this AND gate, so it has both S0, so that means wherever I connected one is from S0 bar I have connected, one in from S1 I have connected, both are 1 1. So and now whatever I2 you feed, suppose if your I2 value is 1, so now your output becomes 1 here. So again your I2 is 0, so again it becomes 0. So assume it has also 1. So now I'll get here 1, so my output becomes 1. So look at here, so whatever you can feed here, even though you have I0 also 1, whatever that may be, or you can make all zeros also here, so automatically all output of the AND gates will become 0. So let us analyze by yourself. So it's a simple. So for other, so that means, so this will work as a 4:1 mux. So inside the square bracket, so square bracket, this is symbolically we are representing. So it has been implemented using gates only. So either using universal gates, so or using a basic gates. So the implementation we have shown it as a using basic gates. So also analysis also we have made here.